same. I would like not to do both of them, but if you want me to do both of them, I'll do both of them. Just tell me if I should do one or the other. Make a decision for me. I'm undecided. You want to do A? Is that good enough? Okay. Now, if I don't want to discriminate, you know me. So I'm trying to help everyone. If you wanted me to do the other one as well, I will. No problem. I don't want you to feel that. Okay, I'm just pressed for time, that's all. So when we're asked to find max min on a given interval, the first thing I would do, I would get the table started with the first derivative and the function. We're not asked to graph. Yes, you can put the second derivative in here, but there's no need because we're not asked to graph. It's not a mistake to put the second derivative in there, but it's not required at this point. So I am specifically told -3 to 5, and that's the only thing I can do. I can only study the function between -3 and 5. Of course, I will plug in the function -3 and 5 in a minute, but I will have to find the critical numbers. So as I saw in your solutions, you got -12x plus 3x squared. We know that there are no critical numbers coming from f prime being undefined because they're polynomials, both of them, right? The function and the derivative. So I will set this equal to 0. I will write f prime of x set equal to 0. And I will write it in the correct order, which is descending order. I will definitely divide both sides by 3 to simplify things. I will factor out x. And of course, I get 0 and 4. It happens that both critical numbers are in the domain. If they're not in the domain, or one of them is not, then I cannot put them. And 0 and 4 are somewhere between -3 and 5. The next step, I will put the function in the graphing calculator and determine the y values for all these 4. Of course, I will also write that 0 and 0 here under 0 and 4 for the derivative. So let's look at the graphing calculator and put it in. So we chose this function. It's 5 minus 6x squared and plus x cubed. And second in table. And I want -3. I want 0. I want 4. And I want 5. So I got the values. I put them in as -76, 5, -27, and -20. And I will study the sign of the derivative between -3 and 0, between 0 and 4, and between 4 and 5. So as you see, the derivative is a second degree function, polynomial function. It has a positive leading coefficient. Does it look like this? You can say, we're not graphing the derivative. Of course, we're not. I'm talking about the sign. Okay, so this is a quadratic function with a positive leading coefficient. Does it look like this, or does it look like this?
Opens up.
Opens up. And it crosses at 0 and 4. Obviously, it's negative between 0 and 4. It's positive outside. I don't have to plug in numbers. It would be a waste of time. It opens up, and it has 2 x-intercepts, one at 0 and one at 4. You can plug in numbers. You don't have to do this. But this is the easiest thing to do. So then, now I check. Remember, these two rows have to work well together. If they don't, I'll say, oops, I made an error somewhere. Okay, from -76 to 5, yes, it's increasing. And that is supported by the sign. From 5 to -27, yes, it's decreasing, and it's supported by that sign. And -27 to -20 is increasing, and it's supported by that sign. So now if you want to make a picture, not a graph, but this will be -76. I'm talking about y values. This will be +5, -76. -27 will be here, and -20 will be here. So something like this. I'm not graphing the function. But obviously, this must be the absolute max, and it's very clear, positive, negative. So it's a maximum. This is a minimum. But it's not the absolute minimum. So I'll start from left to right. -3, -76 is definitely absolute min. There is no other value lower than it. It cannot be local because it's at the endpoint of the interval. Positive 5. So 0, 5 is absolute max, but also local because I can show the open interval. Negative 27 is a local minimum, obviously, according to this. So 4, negative 27, local min. But this one, poor thing, is at the end of the interval. It's not the highest, it's not the lowest, it cannot be local. So I'm going to say 5, negative 20, nothing. So this is the way, remember we had a couple of examples. So this is the way we study a function, max min of a function on a closed interval. Is this good enough? Is this good enough? Yes? Would you be able to do the other one?
Yes.
Say it again. Yes? Yes, Ricky?
Can you go back to the function?
Yes, of course. I can give you this at the end if you want. I also wrote it here. You're welcome. Okay, very good. So now we go back to 4.5. We're going to look at two different situations that we have not seen before. One is a hole in the graph. So I'm going to make up an example. F of x equals x squared minus 1 over x minus 1 times x plus 3. What type of function is this? Of course, we are asked to graph. Graph and show everything. Show all, everything that we know. Limits, asymptotes, and behavior. X and Y-intercepts, first derivative, second derivative, everything. Show all. And graph. So I'll get the table going. F prime, f of x, and the second derivative. And now, what function is this? What type is it? Is it an absolute value? Is it exponential? Is it logarithmic? Is it linear? Is it quadratic? Is it polynomial? What type of function is it? Thank you very much indeed. It was a silly question. I know everyone knows it's a rational function. Of course, we start with the domain. Can anyone give us a domain of this function? Yes, indeed. -3 is unacceptable. 1 is unacceptable. Everything else is fine. Very good. That's sufficient. I don't have to write the domain separately. This is very clear that the function is defined everywhere except at -3 and 1. Then we will try to simplify the function. Let's try and simplify the function if we can. Here it is. We will do what? We will, the numerator, please. So what is, how do we factor the numerator? Excellent, very good. And look what happens next. Or you tell me what happens. I don't want to tell you.
The x minus 1 is cancelled.
Very good. But exactly. But remember, we state the domain of the function before we simplify it. That's why I didn't even touch the numerator before I wrote that x cannot be 1 and x cannot be -3. Perfect. Bless you. So then this is x plus 1 divided by x plus 3. Moving forward, we will be dealing with this function, and this is the function we will be graphing. However, we graph the original function by making sure that the function is undefined at 1, because this function is defined at 1, right? Okay, very good. So now I would like to determine the x and y-intercepts. I would like to determine what happens at 0, what happens left and right of -3, what happens left and right of 1, what happens at -infinity, and what happens at +infinity. Ready? Okay, so let's start from, let's find the x and y-intercepts first. How do I find the x-intercept for any function?
Plug in 0 for x.
So that's,
0 divided by.
yes. So a function to be 0. So x plus 1 over x plus 3 is 0 only when the numerator is 0, which means from here I have x equals -1. Okay, I'll go back. I'll insert -1 where it belongs and put 0. And then I will plug in 0. So for the y-intercept, I find f of 0. So 0, 0, so this is 1/3. F of 0 is 1/3. And I put it accordingly where it belongs. Yes, please, Vanessa.
How did you get that?
Which one?
0, 0, like 1/3, how did you get that?
F of 0. 0, 0, 1/3.
Okay.
Better? Very good. So now the limit at -infinity. Limit from x plus 1 over x plus 3 as x approaches -infinity. Now you can say, I have no idea. But you know that this is infinity over infinity, and you know you have a tool now that we did not have a long time ago. What is the tool I'm talking about? L'Hopital's rule. So if it's infinity over infinity, which it is, or negative, it doesn't matter. Then I have limit as x approaches -infinity. What is the derivative of the top? What is the derivative of the bottom? 1. So this is definitely a horizontal asymptote, y equals 1. There is no point in redoing the positive infinity. I'd never used the sign, really. So go back to my chart. I summarize it. Y equals 1, horizontal asymptote. Y equals 1, horizontal asymptote. And that's the end behavior. Now I want the limits left and right of -3. Limit of x plus 1 over x plus 3 as x approaches -3 from the left. And limit x plus 1 over x plus 3 as x approaches -3 from the right. So what is the case? We always need to find the case. The meaning of what is when we plug in -3. And we know what happens. It's -2 over 0. And we know that this answer must be infinity. But we don't know which one. We did this in chapter 2, a long time ago. Okay, so all I have to do is say -3 from the left, which means -3.1. Plus 3, this answer is negative. The top is -2, and the bottom will be negative. What is the sign on the left of -3? One more time. The numerator is -2, and the denominator is -3.1 plus 3, which is negative. Very good, awesome. And this one is -2.9. The top is negative, but -2.9 plus 3 will be. So then the answer is excellent. Go back to my table. I have positive infinity, and I have here -infinity. Now we're done in a moment after we finish with the limits left and right of 1. So limit x plus 1 over x plus 3 as x approaches 1 from the left, and limit of x plus 1 over x plus 3 as x approaches 1 from the right. Remember, we always have to plug it in first. So what do we get at the top when we plug in 1? 2. What do we get at the bottom when we plug in 1? Good. So 2 over 4 is 1/2. 2 over 4, 1/2. Whole, which is 1, 1/2. When x is 1, the y value is 1/2. Go back to the table and put it in. 1/2, 1/2. Therefore, x equals -3 is a VA, x equals 1 whole. So what is the difference? Here's the difference. After simplification, this factor did not go away. This has to be a vertical asymptote. After simplification, this factor went away. The function is still undefined, but it does not have a vertical asymptote there, but a whole. And this is also determined by these limits. As you see here, it's very clear that this is a vertical asymptote because the right-hand side is positive infinity, the other is negative infinity. But this one, as x approaches 1 from either side, the function approaches 1/2 from both sides. This is not infinity. This cannot be a vertical asymptote. Good. So now we move on to the first derivative and the second derivative. Ready? And we're done after that, but we still have work to do. So remember, our function is x plus 1 over x plus 3. Quite simple. F prime of x. Can anyone dictate what we use and how we use it? Excellent. The top prime times the denominator minus the top times the denominator prime. Right. Over x plus 3 squared. Excellent. So then we have x plus 3 minus x minus 1 over x plus 3 squared. These two go away. -4 over x plus 3 squared. Nice and easy. Critical numbers. After I find the derivative, I have to find the critical numbers. So can anyone tell us what the critical numbers are here? They could, yes, Harvey? Thank you. I would have cried because then nothing would have matched my other row. Thank you. Yes, extra credit, yes. He's negotiating every day. Extra credit. He's right. No, it is 3 minus 1. I don't know. Okay, so it's 2 over. Let me erase it because it doesn't look like a 2 at all. Okay, very good. See, this is what the lazy person is doing. Instead of erasing the whole thing, he's just trying to adjust. I apologize. Of course, 3 minus 1 is 2. Okay, so critical numbers. So this is never 0 because the numerator is never 0. And this is undefined when at -3, but so is the function. So what can you say about critical numbers? No critical numbers. None. No critical numbers. This cannot be 0. 2 over x plus 3 squared cannot be 0 no matter what you do. It's undefined at x equals -3, but so is the function. No critical numbers whatsoever, which means definitely the function does not have what? Max or min. If it has no critical numbers, you cannot have max or min. Excellent. Very good. Can anyone give us the sign of this expression? Forever and always. Excellent. That's all I have to do. Now the moment of truth. If Harvey hadn't told me that that was wrong, I would have been on the wrong track. And then I would have said, oops, what did I do? Okay. So from 1 to infinity, what does the function do? Is that supported by the sign of the derivative? Excellent. From -infinity to 0. From 0 to 1/3. From 1/3 to 1/2. Although it's a tiny increase, it is an increase. From 1/2 to 1. All is increasing. And the sign is, yes, Vanessa?
I have a question.
Yes.
You got 1 on the infinity where y equals 1.
Right. So we use L'Hopital's rule. It's infinity over infinity. When I differentiate this, I get 1. When I differentiate this, I get 1.
I understand that, but you did it to limit as x, which is -infinity.
Yes, I said I'm not going to repeat it because I did not use the sign.
Oh, okay.
When I differentiate x plus 1, if x goes to negative infinity or infinity, it's not going to make any difference.
Okay.
However, the point you are making is very valid. Why? This would not always happen. Some functions do not have the same asymptote, horizontal asymptote at both ends. But here I did not spend the time on that because I did not really use the sign of the derivative. So when I differentiate x plus 1 and x plus 3, I still get 1 no matter where this is going. But it's a very valid point. Thank you. Okay, so second derivative. I will change the first derivative, obviously, into 2x plus 3 to negative 2. Why? Because it's easier to differentiate. So now please tell me what you get. Negative 4 times x plus 3 to negative 3 times the inner function prime. But the inner function prime is 1. So this will be negative 4 over x plus 3 cubed. Do not jump into conclusions other than the fact that this is never 0, which means the function does not have what?
Asymptotes.
It does not have inflection points. The second derivative talks about concavity at inflection points, from opening down to opening up. Very good. So don't jump into conclusions about the sign because I have to rearrange it in order to study the sign. So I'm going to rearrange it like this. Just for the purpose of the sign, because I don't want to spend too much time on it. Which of these two pieces will not affect the sign?
Right.
Of course, this is always hard. Don't even look at it. It's a waste of time. So all I care about is this and the sign in front. So let's go back to the table. Here's my table. So to the left of negative 3. So let's plug in a number or just tell me the sign. To the left of negative 3. Negative to the left of negative 3, like negative 4. What is the sign of this?
Positive.
Yes, it is positive. So negative 4, this will give us a negative with minus in front, will be positive. So to the left of negative 3, this is positive, which means the function opens up. So now let's plug in a number to the right of negative 3, like 10. What is the sign of this piece? Because this doesn't matter. Negative indeed. Which means the function will open down. No inflection points, no max min. And now we are absolutely ready to graph. I don't care for anything else. The function is not symmetric. We should write symmetry also. So f of negative x definitely will not equal f of x, and it will not equal negative f of x. Not symmetric. This will be an even function symmetric with respect to the y-axis, and this will be an odd function symmetric with respect to the origin. But there is no situation like that here. Okay, ready to graph. What do we have to graph first when we graph a function with asymptotes? Always. We have to graph the asymptotes. The function has one vertical asymptote at negative 3. Do not graph it as a solid line, and a horizontal asymptote, y equals 1. Then I will plot the points I have. I have 0, 1/3, kind of difficult. I have negative 1, 0. And I have 1, 1/2. That's all I have. So now let's look. From approaching 1, increasing towards infinity, opening up. From approaching 1, increasing towards infinity, opening up. From negative infinity, crossing the x-axis, crossing the y-axis, going through a hole, approaching 1. From negative infinity, crossing the x-axis, crossing the y-axis, going through a hole, and approaching 1. This is the graph of x squared minus 1, x minus 1, x plus 3. Again, I'm fine if you don't like this table. I will not take credit for it. I was taught this way. Invent your own. But you must summarize the information somehow. So it's increasing all the time. It's opening down, as you see. So summarize the information somehow on your own table. If you do not prefer this one, I'm fine. Okay. I would like us to look at one more type of function, and this time I don't need to make one up. We can choose one because they are here. And they are on page 318. From 65 through 70, that's where they are. 65 through 70 on page 318. I need you to see at least one of these examples. This is a rational function that does not have a horizontal asymptote. Instead, would have a slant asymptote, either this way or this way, but not horizontal. So rational functions cannot have horizontal and slant, not possible. Either horizontal or slant. And there is only one type that has slant. The one with the slant asymptote must have degree n plus 1 over degree n. Any combination, degree 10, degree 9, degree 7, degree 6, degree 3, degree 2. When we divide degree 7 by degree 6, what degree do we get? If you divide x to the 6th over x to the 5th. Why? Because I get a line. If I divide degree 11 over degree 9, what degree do I get? Why? Because I get a line. If I divide degree 3 over degree 2, what degree do I get? Because I get the slant asymptote. That's why that's the requirement. If the degree is here 4 and here 2, I'm not going to get a slant asymptote. Because the degree, when I divide, it will be 2. So only when the degree is by 1 unit higher at the top than the bottom. Those do not have horizontal asymptotes. No horizontal asymptote, but slant asymptote. Or oblique, whatever you want to call it. Okay, so let's choose a problem. What about 65? A simple one. 65 on 318. So this is y equals x squared over x minus 1. So is this a rational function? What is the degree at the top? What is the degree of the bottom? Will it have a horizontal asymptote? No. It will not have a horizontal asymptote. This is the one that has a slant asymptote. We start with the domain and the table. Please give us the domain. Exactly. Everything goes but 1. Awesome. Let's start the table, please. F prime, f of x, and then double prime. So negative infinity, 0, 1, infinity. Since x minus 1 doesn't go away, I already can write that this is a VA for sure, vertical asymptote. Now, I know that I have to find the x and y-intercepts. So this, and this. So once again, the function is this. And let's plug in 0. What do we get? 0 indeed. Let's find the limit left and right of 1. So the limits left, 1 from the left of x squared over x minus 1, and 1 from the right of x squared over x minus 1. What do we get? I already know it's 1 over 0. I already know it has to be infinity. It's a must. X equals 1 is a vertical asymptote for this. I know that. But I don't know the sign. So 1 from the left means 0.9. I need the sign for the first one.
Negative.
Indeed. Very good. Negative. Thank you. Great. So 1 from the right.
Positive.
Excellent. So negative infinity and infinity. That part is done. Okay. Now I need to find the limit and infinity and negative infinity. Limit x squared over x minus 1. X approaches negative infinity. Okay, I have to plug it in to see what it is. Where does the top go? The bottom. I have a tool now. What is the tool? Very good. So I have limit, x approaches negative infinity. The top goes to, I'm sorry, the derivative is 2x, and the bottom is 1. Excellent. Now I'm using the sign of the infinity. So when x approaches negative infinity, where does this go?
Negative.
Negative infinity. In the same way, when limit approaches infinity from the same thing, 2x over 1, nothing will change from this step till this step. Where will this go?
Infinity.
Yes. So negative infinity and infinity. Excellent. We're done with the function. I can't find anything else about the function from the function itself. I'm done. I have to move on to the first derivative. Any questions for me? Yes, please, Vanessa.
Did you just,
I didn't do the differentiation again for x approaches infinity because from this step to this step, I did not use the sign. But from this step to this step, I used the sign.
you just put the two, like you,
You can put the 2 in front if you want, but limit as x approaches negative infinity from x is negative infinity times 2 is negative infinity. And here, yes, Ricky, one more second. So when x approaches infinity, infinity times 2 will be infinity. Yes, Ricky? Sorry. Why? Because when x approaches negative infinity, 2 times x must approach negative infinity.
so you substitute x for negative.
All right, I have to do that.
Oh, okay.
Yes, I have to do that. Yes. Angie, you had a question? Brandon, I'm sorry.
I'm just kind of confused on why you only use negative infinity for when you're trying to find the limit, like in the beginning.
So why I use negative infinity is because I have to check what type of limit this is. So it may be 1 over 1, and then I'm done, right? But I have to use, because I have to determine the end behavior. So it turns out that I don't get a number, because there is no horizontal asymptote. I will get the asymptote that is will be a slant. But we have not determined the slant asymptote yet.
So if the limit as x approaches negative infinity gets you the same as positive infinity,
No,
you don't
it
have
doesn't.
to. Well,
It doesn't.
in the beginning.
From this step to this step,
Yeah.
it's the same process.
So on like that step, it doesn't matter which one you use.
No, it does not. Infinity over infinity or negative infinity over positive infinity or positive over positive, negative over negative, it doesn't matter. Here at this stage, it does not matter. But now when I have to plug it in to get the answer is different. When I plug in negative infinity, I get negative infinity. When I plug in infinity, I get infinity. Is that clear, everyone? Yes? Okay, so now let's look at the first derivative. Let's calculate that. So what do we use? So one more time, I'm writing it here so we can see it again. F prime. Very good. Quotient rule. So the top prime
2x times x
minus x squared times, very good. So this is 2x squared minus 2x minus x squared over x minus 1 squared, which is x squared minus 2x over x minus 1 squared, which is x times x minus 2 over x minus 1 squared. Well, this function has or does not have critical numbers. This function has critical numbers, and they are 0 and 2. Very good. When we set this equal to 0, we get x equals 0 and x equals 2. This function is undefined at 1, but so what? So is the function, so it doesn't matter. So then I go back, 0 and 2, 0 and 2. 0 and 2. I have to find the function value at 2. What do we have? We have 4 over 1, so this will be 4. Now we have to study the sign of the first derivative. See what happens here. Okay. I hope you agree. I'm not going to plug in anything in this piece. I'm not going to waste my time. It's always positive. I don't care. Now the numerator, we're not graphing, but the numerator is again a quadratic function with a positive leading coefficient. So in between solutions, it has to be negative, outside positive. You can plug in numbers if you want, but I recommend thinking in terms of, it's not a mistake to plug in numbers. I'm just showing you a different way. Very good. So now, at the moment of truth, this is when I catch my mistakes. From negative infinity to 0, what does the function do? Is that supported by the sign of the first derivative? Good. From 0 to negative infinity, what does the function do? Is that supported by the sign of the derivative? Okay, very good. From infinity to 4, is that supported? Very good. And from 4 to infinity? Perfect. What type of point is 0, 0 for sure? Very good, because that's the sequence of signs. It's local max indeed. From positive, 0, negative. What about 2, 4? What type of point is 2, 4? Because the sequence of this, or you can see that my arrows. So it is a local min. It could be not, but it could be. But right now for this, for the purpose of the table, we cannot say for sure. That's okay, good. We're done with that second derivative. Although it's very clear what happens here. Let's study the second derivative, which is a little bit of a mess because I have to differentiate this. Do I like that? Not really, but let's do it. Okay. It requires work. Very good. So do not try that, right? You really want that form to differentiate. The top prime, please.
2x minus 1.
Very good. Times x minus 1 squared. Minus.
X squared minus 2x times 1.
Careful. We bring 2 down.
2x minus 1.
X minus 1 times the inner function prime. Luckily, it's 1. I have seen it in the previous test, and it made me cry. And this made me remember that, recall that. Too many of you simplify x minus 1 squared from here with 2 from the denominator. Too many. So we understand that that is not possible, right? Do we understand why? Because this is not a factor in the numerator. You cannot simplify pieces of a term with a factor in the denominator. So that is not allowed. You cannot cross this with this. So please be careful. Okay, what we can do and we have to do, we have to factor out x minus 1. And let's see what is left from all this mess. And look, now I can do this. This is allowed now. because I'm simplifying a factor with a factor. Okay, so let's see what is left here. I have an x minus 1 left, and I have a 2x minus 2. Let's write it first before we multiply it for everyone to see. 2x minus 2, x minus 1. Minus, this is out. Here I can distribute. Minus 2x squared plus 4x. So that is okay. Minus 2x squared plus 4x. Now I will distribute here, see what happens, and then combine like terms. Ready? Ready to continue? Yes? Can you keep up, everyone? Okay. Stop me if you have questions, please. X minus 1 to the third in the denominator. Okay. So 2x squared minus 2x minus, I'm going to erase that, plus 2 minus 2x squared plus 4x. Okay, one more time. 2x squared minus 2x plus 2 minus 2x squared plus 4x. Okay, nice. These two go away. Oh, these two with these two. Awesome. 2 over x minus 1 cubed. So now remember, for the purpose of studying the sign, nobody cares about this. Nobody really cares to rewrite the function. Yes? Did I do something?
I was just making sure. It's negative 2x and negative 2x. Do those cancel out?
No, with this.
Oh, okay. Okay, that makes sense.
So nobody cares about this. The reason why I'm doing it is because I'm pointing out that this piece is positive, so I only care about the sign of this. To the left of 1 will be a sign, to the right of 1 a different sign. And we're done. And it's never 0. No inflection points. Okay, so to the left of 0, can anyone give us the sign of just this piece? To the left, not of 0, of its 0, to the left of 1, like negative 5. What will be the sign of this? Perfect. To the right of 1, like 10. Very good. When the second derivative is negative, we know the function opens downward. When it's positive, the function opens upward. And this is it. We are ready to graph. Not so fast. I forgot to determine the slant asymptote. That's the reason I'm doing this. Okay, so here's how we determine the slant asymptote. Which page am I on? 7. Slant asymptote. So our function is x squared over x minus 1. We will have to divide x squared by x minus 1. We can use the long division. I should have asked before starting. We can use the long division, or you can use the synthetic division. Which one would you like to use? Synthetic. Very good. Let's use synthetic. This would have been for the long division. We can come back and do that too. When you use the synthetic division, we look at the degree of the numerator, which is 2. The leading coefficient is 1. It's missing a term with x, and it's missing a term with a free term. In the box, so this denominator is x minus a. We can use a synthetic division only when the denominator is of degree 1 and in this form, which makes us or helps us identify a. So a is the one that goes, the number that goes in the box. Now, if we divide by x plus 5, in the box, I will have negative 5. If we divide by x minus 1, in the box, we have 1. We bring down always the leading coefficient. We just copy it. 1 times 1, we write above the line. We add 0 to 1, we get 1. We continue. 1 times 1, and we write above the line. 0 plus 1, we box it in. 1. This is the remainder of the division. Again, we divided degree 2 by degree 1. Quotient has degree. Can anyone tell us? When we divide degree 2 by degree 1. Exactly, degree 1. So can anyone give us this answer? This is the coefficient of the, excellent. So then the division is this, of x squared over x minus 1. X squared over x minus 1 is rewritten as quotient x plus 1 plus remainder over the divisor. From all this, only the quotient is the slant asymptote. This goes to 0. So the slant asymptote for this function is y equals x plus 1 slant asymptote. So now I can ask finally, what do we graph first when we are graphing a function with asymptotes? Yes. So in this case, we have a slant asymptote, which is x plus 1. We have, I'm going back to see where my table is, right here. So I'm making myself a note, y equals x plus 1 slant asymptote. Y equals x plus 1 slant asymptote. Why? Because I want to have everything in one spot, everything in the table, so I don't forget. So now we graph the vertical asymptote and the slant asymptote first. 5, 6, 7. I think I'm on 8. Good. So vertical asymptote at 1. Slant asymptote x plus 1. So y equals x plus 1. Can anyone tell us where, when x is 0, how much is y? Perfect, so 0, 1. And then when y is 0, how much is x? Very good. So negative 1 comma 0. So 0, 1, negative 1, 0. 0, 1, negative 1, 0. Y equals x plus 1. So all we did so far, we graphed just the asymptotes. We did not graph anything else. X equals 1 and y equals x plus 1. Now we're ready to look at the table. So the table says that I have to plot 0, 0, and I have to plot 2, 4. So here's my 0, 0, and 2 is 1, 2, 3, 4. I read my table. Opening downward, coming from negative infinity, from approaching the slant asymptote. Approaching the slant asymptote. It's increasing to 0, 0, opening downward, and approaching negative infinity on the left-hand side of the vertical asymptote. From negative infinity to a local max, coming down to negative infinity. No problem. On the other side, coming from positive infinity, decreasing to 2, 4, and going to infinity, approaching the slant asymptote. From infinity to the minimum, and going and approaching the slant asymptote afterwards. So this was an illustration of a rational function with a slant asymptote, not horizontal. Yes? Here? Yeah. It's a line. So for a line, I have to determine the x and y-intercepts. When x is 0, I got 1, y to be 1. Oh. So, and then when y is 0, I moved 1 to the other side. I got x equals negative 1. I needed these 2 points, the x and y-intercepts, to graph this slant asymptote. So this is the function f of x equals x squared over x minus 1. One more time. When rational functions have slant asymptotes? When the degree of the top by 1 unit higher than the degree of the bottom. Because otherwise, when we divide degree 2, let's say 3 by degree 1, we don't get degree 1, we get degree 2. Yes?
So if it's more than 1 degree, then it does not
More-
have asymptote?
No, it does not. So it would only have a slant asymptote when the degree of the bottom is exactly by 1 unit smaller than the degree of the top. Yes, Vicky?
What happens the other way around? Where at
The
the
horizontal asymptote is 0.
Okay.
Yes, if I have degree 2 over degree 3 at infinity, the bottom is more powerful, it will drag it to 0. Now what happens if this is degree 4 and this is degree 1? No horizontal, no slant. Whatever happens. I don't know, we have to look at the example. But if it's more, it doesn't have any horizontal or slant. The function cannot have horizontal and slant at the same time.